Good morning, everybody. Thank you for coming today. Our first speaker of the day is Dr. Reinaldo Rosa from the Brazilian Institute for Space Science. And he will talk for data science and big data and all these things that involve data and computing. This guy is Reinaldo. Your time.
Okay. Good morning, BRICS Astronomy colleagues. So it's a pleasure to be here. First of all, I'd like to thank the organizers, especially Bruno and Ulysses, for the opportunity to be here. So I choose this subject to talk to you about data science strategies for multi-information source astronomy. Because we are working on that in the last, we have been working on that on the last 3 years. So I brought to you, I'm trying to convince you from this talk that for the BRICS astronomy community, it's very important to discuss a new concept. Actually, thanks to China, because I'm going to show why. The concept of data lake, that's a very important concept in the framework of data science for astronomy. So the outline of the talk will be like this. I just go to the context of data science that most of you are very familiar, I'm pretty sure. And then I'll go to this multi-information source astronomy, and I'm going to show some strategy. Of course, this scenario are very, is the big fashion nowadays, trying to bring together the concept of Internet of Things, and that's the main source of the big data. And once you have the big data, we go to the data mining applications, and from a very smart using of data mine resources, we can get knowledge. So that's the framework of data science. And of course, for astronomers, that's the holy grail right now in our science. Okay, so the multi-information source astronomy, I'm going to call this MISA, but of course that's the same that's the same for multi-messenger astronomy. Okay, and what we can list here some strategies. Okay, we can talk about framework systems for multi-information source astronomy, and data lake appears right here in this this first strategic path. And then we can also discuss data center, the concept where we are going to find solutions for management, communication, collaboration, especially involved in the data science platforms like virtual observatories and so on. Also, citizen science is a very important issue. Okay, machine learning, analytics, production, and we can also include the modeling theory, education, training, workforce development. So all those stuff should be addressed by data science strategies. But in this talk, I'm going to talk, I don't have too much time here, so I would like to stress the data lake concept, and to show you very quickly just a glimpse of machine learning analytics that my group has been using. So that's the idea to bring to you here. Okay, so that's for the people that are not familiar with the fourth paradigm from James Gray that we call data science. Of course, it's a common way, because now we are here, okay? We need, what we are doing is data-driven scientific discovery, and it happens in this kind of engine, okay? We have the IoT, big data, data mine, the big data goes to data mine, we have knowledge, and it goes like this, using massively the cloud computing resources. Of course, nowadays, we have another kind of concept. I'm from the field of scientific computing, so in INPE, we are now talking a lot about foggy computing, not cloud computing. We can have it, you know, very special, I don't say small, but special clouding for some applications. That's why I asked you to, Professor Potter, yesterday about foggy computing. Okay, the big data we are facing on, we know that is increasing a lot, so that's just a partial picture. There are the main optical and the light telescopes in the light frequencies. So here we have this scenario coming to 2020 with many telescopes and missions. So we are facing now this transition that's going to the LSST in 2025. So we're going to this 500 petabyte data. And we are able to, in 10 years from now on, get more than 1.1 exabyte data if we consider the main missions that are here, okay, including the space telescopes for the high energy window. What's important in this figure is to pay attention here. Okay, it's in Portuguese. Quantidade de dados úteis. Okay, this is the amount of useful data, okay, in petabytes. And what means that? The useful data, according to Dan Woods, is the data that goes to the concept of data lake. Okay, it's about 25% of the data usually. Okay. Could be for astronomy, it's going to be different. I don't know, but I'm using here this kind of concept. So for all missions that I could have a glimpse of the amount of data, I calculated this 75% and I put here. Okay. So we are facing this big data lake from sky. Okay, many data, so we need to know how to deal with this. And this concept is very important that I tried to convince you. Okay, so what means data lake? Data lake is a smart distributed data information management system. Okay, but of course focusing on big data. The hotspot here is this important issue, the governance protocols on the big raw data. What you are going to find in the most important thing inside a data lake are raw data, but with high quality. Sometimes you say raw data is not a good quality. No, it's not like this. Okay, raw data, but so we need to be able, okay, to define governance protocols to guarantee that we are going to have here very high quality raw data. And the data flow here is going to be addressed by the users, okay, that are flowing inside of the data lake. And here we expect the data science platforms for services, and also data warehouse and what we call fragmented data sets that we call silos. We have two examples for our community, the VO, okay, and also the open universe that Ulysses and Paolo Jomi are going to talk to us after my talk. Okay, let's take a look in this architecture. There are many ways to show you what means data lake. If you go to the internet, you find many funny pictures, okay, with people fishing in a lake, fishing data. So the analogy is like that. You can go to the market, buy a fish, bring to your house, cook that. But we can go to the lake, in a very good lake, okay, fishing and make the food there. Okay, so that's the idea. That's why they put this name. But of course, it's not so simple like this. That's the simplest way to show inside a data lake the minimum requirements we need in this kind of architecture. So we need here two bases here, what we call model, where we can find, for example, machine and deep learning inside the data lake. Okay, all of you are very familiar with keras and TensorFlow, people that are programming Python to use machine and deep learning resources. And here we have the unlimited storage nodes. This is unlimited because we need this kind of resource, automatic data backup, and threshold recovery with easy expansion capability. Okay. After a threshold, we can be able to renew the amount of data here. And nowadays, we have also some resources like the Gluster FS. Some people, a few people in astronomy that I know that are working on the concept of data lake has been using this Gluster FS. But this is very important, the automatic security administration. It's actually, it's quasi or almost automatic, a semi-automatic security administration. And also, we can find the Cloudera and Yearn that are resources from semi-private companies, because they give you, if you want to use it for science and public use, they give you all these resources in order to assemble this kind of data lake. Okay, so that's the idea. Okay, where we can find the first data lake for astronomy, it's from Chinese people. Okay, we have this publication, a recent one, 2017, the design application of astronomy data lake in China. It was the first time I saw one complete data lake. I don't know, actually I don't know how they are using that, if it's in high performance using right now. I didn't talk to them, but anyway, that's the most interesting example I found to show you today. Okay, they show a very, very complete astronomy data lake for the China Virtual Observatory. Okay, so they define this architecture showing here the storage layer. So it, of course, this is the physical layer of the data lake. So we go to the visualization layer based in the clusters, a cluster file system. Okay, it goes to a gel replication of the data, and here we can define a backup storage that's feasible, and I know that. Gel replication is you can distribute that for the whole planet, for all people. So there is no restrictions, okay? And here we have the key business layer, the interface layer, the application layer. So here we find all the resources we need. I'm not going to details here, but just to give you a glimpse of what they have done. And here we have the astronomy data lake service application. Of course, you have the single user here. Okay, we need to be able to do the certification for each user, and the archive and transportation from telescopes and remote data service. So that's the one very complete scenario for data lake in astronomy. If you want to build a data lake, there are, from the McKinsey company, some paths that we need to follow. Okay, the first stage is the landing zone for raw data. Okay, data lake is should be a low-cost, scalable, pure capture environment. And of course, from that, you can say data lake is built separate from the core of information technology systems. Okay, data are stored in raw formats, as I said before. Internal data can be easily complemented with enriched by external sources of data. So it guarantees the flow of data in the data lake. The second stage is about the data science environment. It should be actively used as a platform for experiments. So it becomes a test and learn environment. That's a very important point. The data scientists analyze unchanged data and build the prototypes for analytic programs. Okay. And the information technology organization deploys just enough data governance. Okay. This guarantees what we call high quality data. Then we go to offload for data warehouses. Okay, so data lake is integrated with existing enterprise data warehouse. So the last stage is the critical component of data operations. Data lake is a core part of the data infrastructure. So who is familiar with data lake know that if you are able to show that, it is going to be very important. Okay. So let's now talk a little bit about the multi-messenger astronomy context. Okay. Here is I draw these things just to make things easier. So let's say we have here the electromagnetic wave flow for particle and for gravitational wave. So it means electromagnetic wave detector, particle detector, okay, but of course no photon and no graviton, and the gravitational wave detectors. So light messenger plus particle messenger, light messenger plus gravitational wave messenger, and of course light. We can have, of course, only two here. We can have the GWAR messenger plus light only, of course. What's important here is to discuss when you have many sources and many detectors, the number of data flow that we have is, of course, the multiplication of the number of sources and the number of detectors. One more example from China. Okay, if you consider, for example, LAMOST, let's say it's a Schmidt telescope like this, and it's able to have here around 4,000 objects at the same time here, simultaneously. And from the MISA concept, we have only one source here for each time, okay, and we have the three detectors trying. Of course, the most important concept here is the concatenation among all those telescopes. But the question into the context of my talk is how big can be the number of data flow for multi-messenger astronomy. Even we have one source each time, everybody knows here that we are talking about transient events. And we know that we know that there are more than 1 million transient events per night. So we are talking about numbers probably much greater than this one. So it means that we are in the framework of big data, of course. I don't know, I took this photo from yesterday's talk. I don't remember, maybe it's from Professor Potter. Oh, David. Okay, so I like this because here you put this mastermind here, and I put this data lake just to give you an idea about data lake in my mind. Okay, let's move to the other subject. I would like to talk you just very quickly about this supernova multi-messenger consortium. What we find here are simulations for what you are going to expecting about multi-messenger coming from supernovas, especially type 1a. I recommend also this paper, Deep Learning for Multi-Messenger Astrophysics. So, the cornerstone here is the using of this long short-term memory recurrent neural network. So we are working on that a lot, okay? We have implemented many architectures for deep learning, trying to classify supernova type 1 spectral patterns. Okay, I put this guy here because this is Jürgen Schmid-Huber. He's the father of this LSTM. And we can say now in the deep learning framework, we are in the era of memory. Okay, each works as a memory, each cell in the neural network. And it's very good to multivariate analysis. And from my point of view, that's very important for multi-messenger astronomy. The difference from machine learning and deep learning is for the deep learning architecture. All the feature extraction is made inside of the neural network, okay? And of course, because you have this feature extraction inside, we have more layers, hidden layers. So that's the easy way to show. Of course, there are more special explanation. But we have worked on those data for supernova, okay, coming from different catalogs, samples. And nowadays we have more than 15,000 samples. This is to training one architecture that we call Cynthia. Okay, Cynthia is the intelligent type 1 supernova classifier. I'm not going to details here. Okay, this is the first one we have using with the LSTM network. So we also use the Susan. This is based on a fuzzy system appraiser to pattern recognition of supernova spectra. We got very good results from that also. And we have this deep architecture for supernova identification that we call DANI. This is based on convolutional neural network, not the recurrent one. And this is a very good one. Okay. So the analysis of all these architecture are very good to separate the type 1A spectra in a very quickly way. So we have here the results. We are improving, okay, from one architecture from each other. So I invited you to come to the poster to have a more detailed information about what we have done. Those are my students, okay, Matheus Bento, Luiz Arantes Filho, and Alex Almeida. 3 of those guys are working, focusing on deep learning applications, okay? And that's it. Okay, thank you very much.
Thank you, Reinaldo. Very interesting. Questions for Reinaldo? Yes, Dimitri.
I have a question about main idea of your talk. We have a virtual observatory,
Okay.
which is working more or less good, and the data lake was instrument proposed for virtual observatory. What is your idea? To remove virtual observatory and increase the data lake to a new instrument?
It depends on the instrument, I think. depends on the amount of data and I think in any project where we are dealing with big data using data mining resources, it's better to do that in a data lake environment. Yeah, you can use data lake for that, yeah.
Yes, it's already proposed for virtual authority. Will that change virtual authority by something new?
I'm not sure if I understand your point, but I think data lake is just an architecture concept to guarantee the access for the raw data, but in a high quality data environment. That's true. That's true. Yeah, that's true. That's why I told you that maybe this 25% will be different for astronomy. Maybe we are going to have less data there.
Yeah, what the Remit said that
The paradigm.
we all store raw data and we all take care of the raw data and nobody uses raw data. And that's something that we have to think about because it's always that question, okay, we take the raw data from the telescopes, we make the fast analysis or individual analysis. What we do with the raw data? Should we just discard the data and save the processed one or not? This is a question that you still have to work on.
Can I add a comment to that? So this discussion says two things to me. The first one is that we have to work hard to make the high-level data with very good, what we say, PI quality calibration available for everyone in the easiest way of accessibility possible, because that's what's usually used. Now, discarding the raw data is also an issue, because if tomorrow someone comes up with a radically new idea and wants to test something radically new in an observatory or in a data that is not produced anymore, and you are not going to rebuild that experiment again, that satellite or whatever, maybe we are throwing away the opportunity of making a discovery that was not mature at the time of a mission, but became mature due to new theory or new ideas afterwards. So it's really an issue. I mean, when we throw raw data away, we might be throwing the answer to a question that we don't know, and it's not going to get back. But on the other side, VO and data initiatives really have to focus on getting good quality, high-level data to everybody. Otherwise, we don't use the amount of information we produce.
You can answer all the questions.
No, I just want to comment on what Ulysses mentioned, which is I completely agree with his comments. For instance, in the case of the survey I mentioned yesterday, South Pole, we will have a pipeline, to put data available, to make data available. But there will be some filters, of course. Signal to noise is one of them. Things like that. Signal to noise on detection, signal to noise on the polarization reduction, and so on and so forth. And maybe our intention is to put the raw data available as well. If you want to just rerun the pipeline, with your own ideas and stuff like that. And Ulysses' point is exactly why the main reason why we are just making the raw data available as well, because 10 years from now, we have, if you remember, we have two images on the field because of the calcite block. It produces two images, and of course, if you have extended objects, of course they will overlap. But I'm pretty sure with machine learning, you can kind of disentangle that in some situations in the future, or maybe even as we speak. So I think keeping the raw data is important for that. Yeah. So.
I agree.
I'll be brief, but I think the idea keeping the raw data around is important. And I think the impediment that people have had to working with the raw data is because of the complexity, usually the size of it, the computational resources required to do something with it. But if you make that simple and accessible to the end users, then I think you'll find quite a difference in the way people use raw data and the things I talked about at the cloud environments.
Yeah, that's the main point, right?
If I may add, while you take the microphone too, there is another. Of course, there is also the limitation on the knowledge of the instrument. Yes. So if you haven't worked an instrument, maybe you cannot do so much with the raw data.
As important as keeping the raw data, or at least the level 0 or level 1 data when you have an experiment running, it's to have the data that prepared the level 1 and level 0 maps or data available. Otherwise, raw data is useless if you don't have the software or the checklist to get there. So not only keeping the data, but keeping a log of how you prepare levels from level 0 to level 1 to level 2, which is the minimum acceptable data that you have to make available to users.
Actually, I think when we are going to face exabyte data in future, this should be a new culture, how we are going to work on those data. You know? So I think there is no way to face all those big data without this concept of a data lake.
So now I just continue here.
Thank you, Reinaldo.
Okay, I think you can hear me. Yes.
Yes, we can.
Okay. So try to catch up with the time. So this is going to be one of 2 presentations on something that kind of draws on the things that we have just discussed and were introduced by Reinaldo, which is the Open Universe Initiative. It's something that I talked already about here in the BRICS meeting in previous editions, and it has matured over time. It's still maturing. It's not a fully active business yet, but it's something that has a different potential when it comes to data initiatives than what we usually see around. And that's because this is not only a technical proposal for development or technical activity on data science, but it actually builds on what more grassroots groups have done in creating technology to try to advance a different concept, which was embraced by the United Nations Office of Outer Space Affairs, because the goal of this initiative is not only to improve data science and collaboration in science and scientific results, but also to have an impact in the sustainable development goals and in development in societies, education, and things like this. So I think that this hides a good opportunity for the BRICS as a bloc and as individual countries or institutions to participate and use that to develop the field of astronomy and space science and data science in their countries, and also use the appeal of the UN and the appeal of collaborations that look towards the development to get more resources into the kinds of things that we do in a more than justifiable way. So what is the Open Universe Initiative? If you go to Google, these presentations are going to be online, so you can look at that later. If you go to Google with this number, or if you click on this link, you can see the original proposal, which was made by Italy in 2016. This proposal was made by the government, but was produced inside the Italian Space Agency. At the time, Battistone was the president, and the director that was conducting this thing was Paolo Giomi, who is going to talk to you just after me. And it was proposed to the COPUOS, and then it was welcomed and included among the activities in preparation for Unispace Plus 50, which was the big conference of the United Nations on Space that happened last year, commemorating the 50 years of the creation of the Office for Outer Space Affairs. And it was also included in the Space 2030 agenda, which is basically the space side of the UN Sustainable Development Goals agenda. So it's within the activities of the UN for this purpose, and under the thematic priority capacity building. So that's where the UN gets interested in this. So there are many other countries and institutions that support the initiative. I'm going to mention them after in the different levels. But Brazil was the second country to actually really get involved into this and help Italy through the process within the UN to do this. So we are partners since the beginning. And so the purpose of this talk is to present the Open Universe as an instrument of potential BRICS interest and as an open data infrastructure for perhaps the telescope network that we are discussing. That's a concrete place where this thing could start. So I just put this because by clicking in each of these, when the presentation is online, you can see all the steps, all the official documents, all the official discussions that happen in the UN for the initiative. So you can follow all the process and know exactly where it stands, how it was developed, and where it stays. There were many workshops organized on the scope of the UN, and many VO people, all the, let's say, the Politburo of the VO has participated in most of this. And so you can also go to the presentations on the web. Some are recorded, some are with the presentations online. You can see everything there. There is no step that is not transparent in this process. So what's the motivations for this? So this is a slide that I stole from Roland Walter, which participated in one of our workshops. And it basically, the main motivation for doing this through astronomy, apart from the fact that astronomy is the most exciting science for bringing people into science, perhaps, is the fact that about now, or very soon, we are going to make a qualitative jump in the amount of data that we produce. And the way we do astronomy is going to change. And so the demand for innovation in how we deal with the data and distribute this data and how we use this data for re-impacting society is going to change a lot. If you look at the FAIR principles, there's a lot of pressure for openness and for the information we produce starting to have a bigger impact in society. So this is going to happen now. And here is just some numbers that show the amount of data that different instruments are going to produce in the future. Some crazy things like SKA is going to produce 30 terabytes per year per living professional astronomer, which is just crazy to think. Not a radio astronomer, so not an astronomer that knows what to do with the data, any astronomer. So it's very important. Also an interesting note that I didn't know and learned in one of these workshops that we organized is that to the importance of having a good catalog that's usable and easily accessible with all the software that you need. 60% of the publications from HST data are not from PI, are from catalog data. And why is this? Because the database and the software of Hubble is really good. It's probably the best we have. So that's the impact. Another point, this is taken directly from the proposal by Italy. It just shows the necessity as you increase the amount of data that you produce. If you don't increase the number of users, then the specific cost of the data that you produce increases a lot. So the specific cost of the knowledge that you gain from your data increases a lot. And it becomes harder and harder to justify why we produce petabytes, exabytes of data if we don't increase the number of users and the number of knowledge produced at the same rate. So this is something that we have to pay attention because this can backfire in the community in the future. And of course, the idea is that if when data science started some 25, 30 years ago, there were hundreds of specialists, more or less, that could use this data, which are basically the people working in the instruments. And now we can have, with VO and good PI quality calibrated data, some thousands of scientists directly working with the data. Ideally, what we want is to take this to the order of 10 to the 6, 10 to the 7 people in the world, including interested citizens, students in schools, universities, and of course the citizen scientists, which a recent report from the American Academy of Sciences predicted that are going to be doing fundamental scientific discoveries in the next 2 decades, because the data is going to be available and the young kids are clever in using computation for mining the data. So of course, as was mentioned by Dimitri, all of this is built and is possible because there is already 30 years of work of the VO building infrastructure, computational infrastructure, protocols and things like this. So this is just a project that goes over and gets what all these initiatives for data science are producing and try to refocus it in a different direction. So it's a new player contributing and working with the others. And of course, again, this is just some illustration of, so when we go from data and information, the raw level, let's say, to knowledge, what happens is that everybody can start playing this game. And that's where it starts to have an impact in the Sustainable Development Goals. So basically, if you make a chronological sequence here, that's the natural history of what's been happening. We just want to use this initiative to push this as a new concept and to push it further. So when you look at the UN, it has put 4 pillars for the Space 2030 agenda. These are space economy, so how space can impact economy, space society, so how space can change our society, space diplomacy, how space activities can help us avoid disasters globally and approach nations, and there is space accessibility, which is very important. If you think about since '68, not many nations have truly benefited from the results of space exploration directly. I mean, products have been created, countries are buying it, but there's still only a few nations that really are full-scale spacefaring nations. And so one of the concerns of the UN is really to improve space accessibility. And I believe this can be done in 4 ways. So you can either directly access orbit and outer space. You can develop space technology to be closer to space activities. You can do education in this field, and you can use the data. Data is a concept that is directly related to space accessibility. One of the things that we have to do is to give access to space data to the people. And I think data is a key element of our times in the sense that the technological barriers for data accessibility, two-way data exchange, storage, and processing have been drastically reduced. So we don't have technological objection to doing anything we want with data now. And also data is generated beyond our capacity as a scientific community to produce and convert into knowledge. It's becoming more and more like that. So if we open data, we improve science. And there is another important thing. Data is cheap and sustainable. So Brazil started as a scientific nation through cosmic ray science, which was the same science that appeared in post-war Japan. Why was that? Or that was in the roots of Russian experimental science for a long time. Why? Because it was cheap and it was in the forefront of knowledge at that time. Data today is, I think, is the cheap and the forefront frontier that we have. So it's an excellent gateway for developing science around the world. Of course, with this, we want to impact, and that's the purpose of the initiative within the UN, to impact mostly in quality education, so to answer to this SDG, but also we can think of others, for example, increase international cooperation, and there are some more indirect impacts. So what are the pillars of the initiative? So this is a conceptual talk, then Paulo is going to come and show what we have been doing of concrete after me. So the first one is to increase transparency. So to work already in the lines of what VO is doing and other data initiatives is doing, ESA Sky, or all these things are doing, to increase the transparency, accessibility of data, and the usability of data. So this is very important. We, for example, had some good discussions with people from Wolfram Research, because when Stephen Wolfram was here, I presented this to him, and he said, that's an interesting project, and how, for example, we can combine some Mathematica-based technology like semantic searches and things like this to VO and the things that we do to data accessibility. So really to think broad, and not only on what we can do in our labs, but how we can get more partners to really increase data accessibility. Yes, this is something that the UN gives a lot of leverage and bargaining power for. The other aspect is to resurface data. We have lots of medium-sized, small-sized telescopes that produce useful data, especially in the follow-up multi-messenger, multi-wavelength era. That's not used. Why? Because there is a difficulty to put this data on the stream, on the lake. So the idea is to work actively to identify which countries in the world have the need to have some help and which institutions can use some help of us and of the UN to bring this data to the fore. So what you are missing, software, let's try to develop software together to answer to your needs. So let's try to bring the data that's being produced, maybe in nations that don't have so much tradition, but can boost tradition if their data starts to be used. So there is really a concept of service here, of looking around and saying, how can we help you come into the game strong? And the last one is to broaden the user base. If you do both of these, and especially if you increase accessibility, then this is easily done, because you can then team up with universities. Paulo last week was doing a course at the New York University of Abu Dhabi using these tools to try to help to bring this data into the university teaching programs. We can partner with, for example, the Office for Education of Astronomy that's been created by the AU, or schools to create applications for astronomy. Of course, we don't do all of this ourselves, but through the UN, we can bridge these collaborations and provide the data that's necessary for then other groups to develop initiatives for this. So the idea is to build something that then can use the UN to create many connections and interfaces to increase collaboration. Now, let's come to the BRICS. So this is something that one of our funding agencies for education and science, CAPES, has paid for a study in 2017. And these are some of the results. It's very interesting to see. This is research in Brazil. From all the research topics, space science is the one that has the most impact from our country, impact in terms of research visibility. And this is very, very impressive. So when we talk about doing something in space science, we are really on the right place, because we have a big impact. And if we have a big impact in science, we're going to have a big impact in society, in capacity building, in STEM education, and etc. Yes? Space science. And another very interesting thing here, I was surprised by this, I had no idea. So this is a measure of the citation impact of the cooperative research between Brazil and many other countries. It includes the US, for example. We produce lots of papers with the US, but they don't have much impact. Now, we don't produce many papers with China, we don't produce many papers with Russia, and we don't produce many papers with India. South Africa is not in this list for some reason. Maybe it's not that significant in terms of papers. But the impact of the papers that we produce with China, Russia, and India are super high. So much so that there was a recommendation by this report produced for CAPES that we improve cooperation with the BRICS. So this is online, anyone can see, it's here. It was asked by our institution of Brazil. Of course, this is in all fields. I don't know if in astronomy that's exactly the case, but of course there is a case there for us to land on and use arguments. So it would be interesting to get this data from the other BRICS to see if this repeats. My guess is that in so many fields, although we are an heterogeneous group, we are in a level of development and level of local problems or local issues that is common. So we have to find common solutions for many things. So, so for example, when you think about STEM education or improving data science, capacity building, I'm sure these are topics that we all have the same issues in our countries, even if we are heterogeneous and in all senses. So this is a good point to rest on. So that's why I think we should work hard to get something together. Esta Kalani was saying, he's not here now, he's probably at the beach. He said he had a teleconference, I don't believe. And but in any case, I think that goes in the direction of the things we were talking, and maybe we should talk about this tomorrow when we sit down together. So in one of the panels, in one of the last meetings that we had about the open universe, Jim Green, the chief scientist of NASA, was there, and he made a comment about open universe. He said, this is very interesting because it has the capacity of, or has as a focus, improving South-South cooperation. South-South doesn't mean only Southern Hemisphere, but it means not Europe and not US. So usually we cooperate vertically. No? The idea here is that we develop something in which we can cooperate among ourselves, and that's exactly the point of this group. So this goes in that direction as well. And so why do I think particularly open universe is interesting for us? Because we have, as I said, a good number of medium and small astronomical facilities. that can profit of boosted productivity. Of course, we have large facilities as well, and this is another thing to add. We are inserted in large international projects, either abroad or as hosts, but we lack some direct leadership in large international collaboration, so we could use our group to achieve that. And we have a varying degree of direct space accessibility and capabilities, and therefore there is a great potential to use initiatives such as Open Universe or whatever initiative driven by data and by science that we do here to boost the space program in our countries, either by education, by attracting people, developing capacities for the 21st century, whatever. And we have this need for increased dissemination and advancement of knowledge and improved human resources. So the idea is to bring the BRICS inside the SDGs. And what's my concrete proposal? So in the context of the BRIC flagship projects, we would like to advance the discussion of a proposal for dealing with the data within the BRICS that includes the Open Universe initiative. So, for example, we have written, we means CBPF, INPE, ISON, and the Purple Mountain. We have written a project for the current call. I don't know with the 7% approval rate if we have any chance, but it's still. This helped us to organize a collaboration. It was for an optical transit network. That's fashionable. It's the good way to go. And the idea was that at least part of the information technology for the project, data center and things like this, was going to be provided by Open Universe. So the data would be available through Open Universe, because then it has a direct window for impact in education and things like this. And I think that something like the Open Universe has an interface with at least 2 flagship projects. We are going to hear about the third one now, this afternoon or after coffee. And this initiative can be a two-way cooperation for 2 things, I think. First, to boost the profile of the Open Universe within the UN, which is a political and diplomatic business, in the sense that the BRICS countries are very strong. So, by the participation of the BRICS countries, this project and this program within the UN can only gain in profile. But as a return, if we have a well-organized activity within the United Nations, clearly our bloc becomes stronger and its sex appeal increases. Also in the ministerial discussions and everything. So I think there is something for both of our groups in a sense. So for the UN and the Open Universe Initiative, and for the BRICS to gain from this partnership. And membership to the Open Universe could be an institution that wants to get involved, a country that wants to get formally involved, like Brazil, which sent, the federal government sent a letter to the UN formally supporting the initiative and things like this. And it can be groups of people that want to get involved in working groups. Anyway, it's many ways to get involved with different levels of formality. And so the Open Universe Initiative, it has not yet been formally funded within the UN. It's, not funded, founded. The foundation is going to happen in the next months. And in fact, the first meeting of the steering board is planned to take place in Brazil as one of the countries that has participated in its construction, also from the diplomatic point of view with the foreign office and everything. And the idea is that there is going to be a steering board that's going to meet with UN and decide what things to do for the year, what initiatives to build. So the UN is very good in capacity building. They do initiatives all over the world. And we want to take the data science of astronomy and space science into these capacity building initiatives of the UN. And there is going to be a distributed infrastructure, for example, of data nodes, of data providers, of groups that do software development. And these are things that we can do for our research, do in the context of our participation in VO and whatever, and just put in this context in a way that is framed to ease accessibility and ease usability by everybody. So it changes a bit, because if you go to a VO platform, a student cannot easily use that. A teacher in the school has a limited use for it. The idea is to take things a bit ahead and take care that everybody is going to benefit from this data. And so you can just reframe a bit what you already do and put this in this context. And of course, you gain visibility, you gain impact, and things like this in your research. You don't have to change what you do day by day. And there is going to be some working groups. For example, we can already envisage that there's going to be a working group dedicated to capacity building around the world using the tools that we develop or tools that other people develop. And are open tools. Development of tools that we think are needed and important. Infrastructure for the data and database. And so the coordination is going to be with FUNOSA, at least in the beginning. Then it can change. Then it can rotate between countries. But in the beginning, the United Nations will have the coordination to kind of give the direction. Then the idea is going to only do secretariat after. And the proposal was originally from Italy. Some countries that are kind of founding members, Brazil, Argentina, and Armenia, have, do you know that the president of Armenia is a physicist? So he very, very quickly jumped into this. And ISON is a founding member at the Sheffield University in the UK. And there is some associated activities with the University of Jacobs University and Technische Universität in Munich, the New York University in Abu Dhabi, and the Purple Mountain has joined the project that we submitted, which has Open University in it. And we have also support from GRULAC, which is the group of Latin American countries in the UN, formally supporting, and Uruguay also formally supports. So now Paulo is going to talk. So this is some kind of initial portal that we made for the project. It's everything in its beginnings, and we don't have formal source of fund yet, but it's shaping up interestingly, even without that. And we are going to hear from Paulo Giomi some of the things that we have been doing, and initially are impacting also a lot on research. And so thank you very much. I mean, these are the contacts, myself, Paulo, and you can, if you want, write directly to the officer at the UN who is dealing with us, with the project. So that's it. Thank you.
Questions?
Thank you, Ulysses. It's very interesting initiative, but I have a question. What are you waiting from us?
Sorry?
What are you waiting from us from this working group?
Okay, so my idea is that, so there are two things which are important in the level of developing the initiative. One thing is that people who get interested in this could either try to formally get the involvement of their institutions or their countries. This is an important thing.
And you should understand that it's not our level.
Yeah,
any activity under United Nations umbrella, it needs a government decision.
Of course, but I mean, I've been going to the United Nations for the past 4 years, so I know the people from the countries that are sitting there. But of course, the people are not going to act if there is no interest from the countries. So some countries, it happened through, for example, Brazil got involved and Argentina got involved because the scientists said, we are interested in this. Then there was, of course, some talks in the high level that supported this, and the thing went through. In some places, for some countries, we managed to get contact direct with the foreign representatives, and the foreign representatives kind of asked the communities, are you interested? Do you want to join? So this kind of connection with the representatives, we can also facilitate that. And the UN is here for that. So the UN office is also doing this connection between the scientists and the representations at the UN for kind of getting this moved. Okay. So this is one thing. The other thing is, this is the political, diplomatic side. But for the science, I mean, this is a project that is starting and is open for collaborators. So if you have an instrument that can provide data, that you are happy that it be available through this initiative, we can provide the data infrastructure for it. If you have ideas of softwares that can be useful for
Ulysses,
impacting on...
okay,
yeah.
okay.
Yeah,
Look,
yeah.
all data that we have belongs to country, to government.
Yes, of course.
So you cannot spread this data without any agreement with government.
Exactly. That's
so
why the first
correct
part is
way
important.
it's to install this open space, and after that, the representative will spread this information to the scientific people in country, and after that you get the answer, yes, we are interested or not interested.
Yes, exactly. Exactly.
Because now you are pushing us to accept some decision that the working group.
And because this can be an extra layer that can impact on the activities of the working group for education and development in a context that can be official in a governmental level. So it's not a push, it's an invitation to, yes, exactly.
Yeah, so thank you very much. An excellent presentation. I think it's a very, very interesting initiative. I have 3 comments. First, I think there is a tremendous opportunity for a link between this and the flagship proposal on big data, because one of the themes that we want to approach is the socioeconomic and larger benefit of democratizing access to big data to the broader community. So I think I'd be very interested to talk to you about how we might operationalize that kind of collaboration. On the other side, 2 weeks ago I was at a meeting at the Alexandria at the library to discuss the concept of an African open science platform, and these very same kind of considerations of how to energize the sort of underdeveloped nations in Africa and the very young population to bring them into the sort of the data environment and allow entrepreneurship and access to data were on the table, the same kind of things you talked about. And that project is now going from a concept phase to an operational phase, led from South Africa. And so I think it would be also maybe good to have a little chat around whether we might align these kind of initiatives and bring South Africa into this project in a substantive way.
Yes, I'm sure. I mean, this is one initiative that is within the scope of the UN. But I think the idea of the initiative is not to substitute or to compete with any other. It's actually to help to viabilize all the initiatives that go in this direction. In fact, I think one of the powers and the interesting things of the UN is that then it can work with the governments and the industrial partners, education, private partners also, to try to help other initiatives that go in the same direction to flourish through cooperation. So I think it's, I think the idea of this is to do something by ourselves as well, but it's to help that other things can also go in the right direction. I think there was a question there. Well, I think the VO is a set of tools that is created for enabling open data, open science, shared science in astronomy. We are going to use the VO as a tool. As a result, if you can see, if you could see the previous slide, okay, we have a logo saying VO inside. So the idea is also that by using VO as a tool to do things that impact in society, to go back to the funding agencies and the governments and say, look, VO do something that is important. So keep funding them, because through the things they do, we can create other things that have an impact in society. If there is no VO, there is no open universe, there is no African open data network, there is nothing. So the idea is to use the VO with a different perspective than the VO developer. The VO developer is going to think of something else. He's not going to think on capacity building, but we are going to think on capacity building. So we add a new thing with the VO tools that then VO can use and say, look, we enable this, and so keep funding us. So I think that's an important thing, because we know there is funding issues with VO everywhere.
Okay, thank you, Ulysses. We will have some time later today, to discuss more these questions. I will invite our next speaker by Skype here. vídeo, né?
Hi, Paulo, do you hear us? We don't hear. João. We are adjusting the sound here. We cannot hear you still. Okay, very good, very good. Oi? Deveria estar ouvindo o som. So we still don't hear you, but we are adjusting. I think maybe the issue is on our side. Deveria estar saindo o som, João? Oi? Can you check your sound, your microphone? Não está ainda, não está ainda, não está ainda.
Tá.
Ah, viva a voz com o mudo ativado. Não pode mexer nesse daqui, é dele. Ah, ele está mexendo. Por isso que deu. Ok, Paulo, wait a bit, please. Vamos ver, ele vai ligar pra gente, aí a gente tenta responder.
Hello?
Okay,
Okay.
we can hear you, yes.
We good now?
Yes, yes,
Okay,
yes, yes.
fine.
Okay.
It was just the way it was started. Okay, so if you give me the go-ahead, I just start. I share my screen and I start my presentation.
Well, thank you for joining us. And
Okay.
we are here very good. And please go ahead. And when it's about for 10 minutes for time, I will give you a hint. Okay?
Okay, so I just start. I assume you see the title of my presentation. So I will be continuing discussing about open universe, starting from the point where Ulysses stopped, essentially. Just let me just show very briefly one summary of what Ulysses has been saying. Open universe is something that is more or less 3 years old. It was proposed 2016 by Italy, but then quickly not only was welcomed by the Corpus, but also other countries like Brazil, Armenia, Argentina, GRULAC, and other institutions.
Sorry, Paulo, sorry. are we supposed to see something on the screen, your slides? Because we don't see.
Yes, yes. You should be seeing my, okay, sorry, maybe now.
Now we see our, yes, okay.
Okay, so sorry, it was my fault. I didn't realize it didn't start sharing the screen. So anyway, this is what Ulises said, that we have cooperation with a number of countries and institutions around the world. And another thing that is very important is that the Open Universe, by definition, is inclusive and it welcomes the participation of any other countries. So I will show you some of the technical and scientific developments that have been taking place over the last 3 years or so. So first is the Open Universe portal, which is something that was built at the Italian Space Agency. It is at the moment the official entry point for the scientific activities of Open Universe. It's essentially made of two parts. One part is the one highlighted by the red rectangle here, and it's just a bunch of pointers to different sites. Like in this case, if you go to space astronomy, you can get links to many satellites and places where you can get space data. There is no time to go into much detail. I will show only you another case of ice cube, the gold bronze event. That's the page where you get the announcement when an ice cube neutrino is, can be followed by the people. And of course, there will be many, many more. Then there is a second part of the portal, which is kind of a different approach, different entry point. You have to specify a position in the sky or the name of a source, in this case, 3C273. You just type the name, and then what you get is something like this. This is a kind of a shopping mall where there are different shops of different colors. Each shop, like the blue shops here, or the green, or the red or yellow, so have some products. Each one with its own trademark and its own specialty. Like in this case, is the ISO product. So you specify the 3C273, and by clicking here, you can get some data that is available at the ISO, actually here down the road. In this case, you can see 3C273 and its jet here. But of course, you can get many other things. As I said, the blue shops are surveys and images of the sky. There are many others. There are some other type of shops, like in this case, this is the SSDC archive, where you actually get data. In this case, you have space data, like in this case, ROSA, but we have 320 observations of Swift and Beppo and so on. This is the SSDC in the Italian Space Agency shop. They give you what they have. They already know that you want data from TC273. Maybe you want to do something more specialized and you want to combine data from many different places. In this case, you can go to the data-intensive shops, like the yellow ones. This is the VOU ICD. I will show you in a moment what it means. It combines data from many, many different catalogs. And this is a CD. This is the spectral energy distribution. This is the intensity, UFU, and this is the electromagnetic spectrum from radio, millimeter, optical, UV, X-ray, and gamma rays, and so on. There's a lot of data here coming from many different places. You can click and get all the data that you want. Actually, this is a kind of an old version. It gives you the facts and the database, and also the reference to the data. In the current version, you also get the timing when the data was taken. So you get spectrum and timing information. This is a more advanced tool, and it gives you a movie of the spectral energy distribution. So you can have time that goes by here, and this is just a picture. But if you run it, then the time goes by there, and you see that the colors change depending on the timing. You see how the SD changes with time. So this is a way of putting together an enormous amount of information in the spectral and time domain, and visualizing in a very new way. We have many, many other examples, and there's no time to go into much detail. I will speak about now about something that is beamed at more or less science. To show you what we can do with Open Universe. So we started a number of things, Open Universe for Blazar, but also for other things. So this is one project to get to serve the Blazar community using the tools and the data available in the Open Universe. You click on the front page and you get here. We have a master list of Blazar. For instance, we put together 6,000, more than 6,000 Blazars here from different catalogs, the BZCat, the 3HSP, which is just published, 3 lakh, and the newly published 4 lakh catalog, for a total of 6,000. And you can get the data, access the data also in an interactive mode. This is a tool, and you will see examples of these tools that are based on new technology. In this case, it's called VOU Blazar. VO because it's virtual observatory. It is basically it's built on top of the VO, and it's also an Open Universe because we've been thinking about that. And it's a tool that is developed to facilitate the discovery of Blazar and to build energy distribution. In this case, here at the bottom, you see the error ellipse of a gamma ray source. We don't know which one of these, the red points are radio sources, the blue one are X-ray sources, and there could be other sources here. And the tool goes around the world using the VO protocols to get information from 35 catalogs, and then it combines the information, and eventually it will put also some machine learning technique. At the moment, is a algorithm that identifies possible counterparts. In this case, it's a blue object, which means it's a particular type of Blazar, and it's this one. And then you can click on it, you can get the SED. This is an example of beautiful SED that you can get, but this is an example also of the fact that there are different services to get this sort of data. Again, this is the radio, these are millimeter data, then optical, is an enormous amount of optical data of different colors. The red colors come from the SSDC ASI tool, which is strong here. The green one comes from the VOU Blazar tools, which interrogates different catalogs. Here you have a lot of data in the millimeter here, and lots of variability here in the X-rays. And then we have some kind of light brown data, which I had to take manually out of the web. It's data that is actually available, but it requires some manual intervention. So if you put together everything into a single service, and then you will get an enormous amount of data for everybody with a single click. This is something that addresses directly something that I was listening before on the YouTube channel. You were talking about analyzing data directly from low-level data, and how to do that. And this is called Swift Deep Sky in a Docker container. Docker is a new technology, kind of an emergent technology. It's a kind of a light virtual machine that runs on Macintoshes, Linux, Windows, and so on. And we have encapsulated all the expertise that's needed to run a sophisticated Swift data analysis from raw data to final products into a Docker container. So all the expertise is encapsulated there. You don't need to know anything. And this is one possible solution to the problem that I've been hearing before. So all you have to do is to specify a position in the sky, right, the section and declination, and at which time the observation were done. So the system goes to Goddard and it finds out automatically, you don't know what's happening. Low-level data, the meta information from Goddard, the data from the UK or from Italy or from Goddard, depending on which one is less busy. And then the data is automatically downloaded to your machine, and then the complex pipeline is run based on HERSOP 6.25. And the results are written either to your computer, or you can even upload the results to a database that is available to everyone through the Open Universe things. I will show you some example of something that is running actually heavily on a machine in Abu Dhabi in a moment. Okay, so we use this to build something scientific. So since we are talking about blazars, we said, okay, let's take all the available Swift data on blazar and run this Swift Deep Sky. So I just downloaded the position and I ran Swift Deep Sky on a number of machines on 11,000 objects, on 11,000 observations, and I built a database that has been that now has been published on astronomy and astrophysics. And all of this includes flight information, spectral information in 3 bands, and timing information. Next, again with Swift, this is not yet on a Docker container, but it will be in the future. This is the same, but using not an imaging tool, but the spectrum analysis, full spectral analysis. That is useful when the objects are very bright. So we've been doing that for the more than 100 blazars that have been, on a certain number, I think it's 39 of blazars that have been observed more than 100 times. And the results can be available of this spectral analysis online in terms of light curves, and like in this case, but also spectra. We're very building this way a very rich database of spectral and timing information. The results are also available in a graphical form, in an interactive way. Here, this is a page that you can reach. You can specify here your object, or all of them if you want. In this case, it received 454.3, and you get the light curve here. Down here, you get 443 spectra, and for each spectra, you get the photon index, reduced chi-square, the log parabola parameters, and all the other parameters. And you can play with the data also in an interoperable way by piping the data directly, for instance, to TopCat. You click on here and you pass the data to the TopCat, and then you can use the tools of the VO to continue looking and inspecting your data. It's just an example. Another way of making public data, all the data from Fermi is public, and it's easy in principle, but it's very complex. In this case, you see a beautiful light curve from a blazar called the CTA 102. This is a light curve built using a technique called adaptive bin light curve. That is, the size of the bin depends on the intensity of the source. The higher the intensity, the shorter the bin, so that you get all the information. And we will do that for the 30 brightest blazar in the sky, in the gamma ray sky. Take into account that to produce this light curve, it took 3 weeks of CPU time. So not everybody can do that, but we can do it for them. And then you can click for examples of light curves, like in this case. This is a graphical user interface. Sometimes the light curves are very dense and it's difficult to find out what's going on. So you can with your mouse specify an area, and then you can zoom up, you can pan, you can move, you can do a number of things. This is just a graphical way of presenting data. This is another thing that is quite interesting. This is a survey that I've done in 2 days, actually, using 2 machines in Italy, different parts of Italy. I thought I wanted to do a survey of the X-ray sky using Swift and using the Docker container I've done before. So what I did, I thought GRBs, gamma burst, exploding random position in the sky. So and this is the one example, this is GRB. But if you remove the GRB, you see that around the GRB there are many, many other sources. And this is a completely unbiased survey of the sky, GRBs explode in a random way in the sky. So this is only one, but if you multiply by 1,000 that have been observed, or more than 1,000 have been observed by Swift, then you get, like in this case, you get a survey, which is this green thing here. This is how this survey compares with existing surveys. This is the area of the sky. This is the full sky, and this is the intensity in this particular band. So at very shallow sensitivity, there is the Rosa all sky survey, and it's all sky. But then, if you want to go from a few 10 to the minus 13 to 10 to the 15, then immediately you go to a very small area of the sky. And our survey covers this part here. This is the expected coverage of the Rio Zeta, which was launched about a month ago. It will cover the whole sky by a factor 20 or so below Rosat, and then it will not cover the entire sky at lower fluxes. Now, when I was so I've done this, and to validate it, I calculated the log-n log-s, and it turned out to be identical to the log-n log-s. I don't have it here, but I could show if somebody wants to see it. I will publish it. The log-n log-s is exactly identical to the one done by XMM and Chandra. So the quality of the data is quite good. So when I was last week in Abu Dhabi, New York University, these people never been working on X-ray astronomy. So I said, why don't you, instead of running this processing on GRBs, why don't you run it on all the Swift images? In that case, you get a survey like this. There are about 15 times as many pointings in position different from GRBs. So this the green one is actually the measure sensitivity. This is the expected sensitivity. Now, they started doing this, they knew nothing about X-ray astronomy before last week, and they already done 30% of the sky in 3 days. They can run about 10% of the sky with a single machine in a place where there was absolutely zero experience in X-ray astronomy. And this tells you how this new concept of encapsulating the complexity into a Docker container can empower people who have no experience in doing something very competitive. In particular, you see here where the two lines cross. Below this flux, which is about, okay, thank you. I seen it, which is about 7 10 to the minus 15. Here, this survey is actually better than the Rio Zeta. Okay, then that was for gamma ray burst. We're doing similar things for GRB. There is no time to go into details, but we're doing something similar. And of course, while we are producing data for everybody, we're also publishing products. And since one of the themes of this workshop is multi-messenger astronomy, I will talk in the last 5 minutes or so about ice cube neutrino tracks. We here in Germany, we've been looking at neutrino tracks, which actually are distributed this way. You can see that the distribution is not uniform. This is the galactic plane, and this is where the neutrino tracks are. And this is because the ice cube is not sensitive in a uniform way to high energy neutrinos. For various reasons, there is no time to go into details, but this is what it is. So for every one of them, together with a student of mine, Theo Glau, we are devising something that is based on the open universe, and that is something that could be an example of how future or imminent products, what can be done using the power of transparent data and easy availability of data. So when a new track is coming, there is a GCN is issued. There is a program that reads all the GCNs, and immediately when the position comes, the pipeline starts at any time of the day, and then you automatically get the VLU blazer. In this case, you see here this is the area, the 90% area, and the red points are radio sources, the blue points are the X-ray sources. There is one source here, which this diamond, which is a blazer of a certain type. That could be an interesting object, although it's slightly outside the 90% of the circle. It could be interesting. So what the system does, automatically it looks for the so-called TS map. This is the probability that the source is actually there within a few days of the event using public data in Fermi. And on the right side, we have all the Fermi data, 14, 13 years or whatever it is now, compared to the presence of the blazers that have been detected by the blazer. But immediately, when this happens, it's about 1 minute after we get the GCN. So we know that instead of that there are some interesting places around the neutrino where telescopes can point. Now, Swift points in a random, we're trying to cover the entire field of view by pointing in many different directions. That's very expensive and very costly in terms of telescope time. But if you know that there are special places like this one, where there is an interesting object, instead of going around the entire very large data arrow circle, you can concentrate in there and maybe also do the rest, because you never know. And then you can optimize your time. And then the tool gets data from radio to gamma rays and does on the right here, you see the radio data here. This is an event that actually happened in 2013 when the radio was almost 2 Jansky. The X-ray data, which is the blue one, nobody bothered to observe this object when the neutrino arrived. And the gamma ray data, which is down here, is going up and down, as in many other cases. This is a very bright 2 Jansky at the peak blazer. And if you look at the SED, it peaks here, which makes it an intermediate high energy peaked object. You see here that it's still, the X-rays are still, in some cases, they are still steep, which means the synchrotron arrives in here. But the very nice thing is that the gray spectrum is the average spectrum, but the red band tells you the spectrum during or around the neutrino event. In this case, you see something funny happening. Instead of the spectrum, instead of going down, there is a high component there. And this is the level, the energy level of the neutrino. So all of this is done in an automatic way. And within a few minutes, you get some information. And then as the data comes in, you get more and more information. At this point, other telescopes, like in your network, can provide some more information. And then that information can be added to the tool to the benefit of everyone, or you can keep it private for yourself. Okay, and this is something that, this is the kind of a web page that can be consulted very easily on your phone. So what we will be doing when a new event will come, we will issue a tweet, and anyone in the world that follows us, they can find, thank you, I saw 5 minutes, anyone in the world that can follow the event and maybe even contribute in providing data. This is something very, it's a quick look that is available on your phone, but if you want, there is a PDF file which is always associated where the analysis is deeper and is explained in detail. So there is something that is going on. That's just an example of how to use in a modern way the power of easy availability of data. This is another way of broadening the user base, as Ulysses was showing before, trying to make other communities benefit from the data. We are a community of scientists, which is a few thousand people, maybe 20,000, maybe 50,000. The world is much bigger, billions of people. And in principle, if the data is easy and available, anyone can benefit of it. This was one way of going in that direction, is to have workshops. One such workshop happened last, not this one, but the previous Sunday. The Sunday for them is Monday. So at the New York University in Abu Dhabi, and we had a lot of the students, both from Abu Dhabi University, New York University in Abu Dhabi, but also from Sharjah University and other places, and other universities in Abu Dhabi and Dubai. So there is quite a lot of interest. And as I told you before, nobody knew how to use X-ray astronomy, but they are now doing probably one of the best surveys that can be done with the data available today. So people can go from zero to be competitive with the best scientific data in the world very, very quickly. So this is my conclusion slide. We try to demonstrate that the space science data for everyone is possible, and with a few ideas and without too much money, I think we demonstrated that this is true. Sustainable cost, of course, when we went to the UN, and many people criticized us, saying that it would be, it's a nice dream, it's a utopia, but it costs too much. I think we demonstrated in these 3 years that it's maybe it's a dream, but it's doable. It's something that can be done without spending too much money. We can handle big data. Yes, there's an enormous amount of data around, and I think with good ideas and with good technology and taking advantage of existing infrastructure and emerging technologies, we can do quite a lot. And then we can train people based on workshop and so on. So all of this can be done, as we said, in those workshops at the United Nations, using minor modification of agencies' cost to completion models. An agency consider its duty done when the data is given to the PI. But that's not the end of the story. We can do much more. So we have to do a modification of that model. And we say it's minor only in cost, because the cost, if you already invest 1 billion to build something like a sophisticated satellite, the cost to go from the current level and to bring the data to everyone, the data is a very, very small fraction. So it's a really, in terms of money, it's a very, very minor modification, just a cultural thing. Use of existing infrastructure, for instance, International Virtual Observatory Standards, use technologies and good ideas. And finally, let me repeat, the Open Universe is inclusive and welcomes the participation of any other country. So this is all I wanted to say, and thank you very much for listening to me.
Thank you, Paulo. Questions, please? Yes, Antonio Mario from the University of São Paulo.
Yes, thank you for your talk, Paulo. Very nice. Congratulations, very impressive. Couple of questions, if I may, very, very quickly. I'm not familiar with the Docker that you mentioned. In the end, you mentioned it's a Linux container. Is that something particular to Linux, or it can be used in any OS?
Okay, Docker is based on Linux. That means that whatever software that you're running has to be running on Linux. However, once it's encapsulated, it works everywhere. So essentially all you have to do is to do a Docker container, and then anyone using a Mac, Linux, or a Windows 10 machine can click, download the code, and it will work straight away.
Okay, thank you. The other comment I would have, as a professor, a former teacher in high school as well.
I'm afraid I cannot really listen very well. There's some noise. Okay, maybe if you speak slowly.
Okay, sure. Can you hear me now?
Yes, yes.
Okay, great. Yeah, just a comment.
Yeah.
I think the software that you showed in the for blazers and stuff like that is fantastic, and it's basically a ready tool. I'm thinking about the high school students, the last 2 or 3 years of high school. There'll be certainly for undergrads, possibly for high schoolers, in the last couple of years maybe, but to make them a little bit easier for them. You might, just a suggestion, I'm sure you may have thought of that. It would be interesting to add some, for instance, in the text that you were explaining I think the Blazor tool, I think it was. There were many, for a high schooler, it would be technical terms that you will have to add links to, explaining what a spectral energy distribution is, etc. Like variance and terms like that are very apparent to us, or to maybe undergrads, but for people in high school, of course, and maybe last few years of elementary school, even for very bright students, they would need help in their language and also in explaining. But mostly, my point is explaining those with some links, extra links. What those terms mean. Just a suggestion.
Yes, absolutely. One idea that we've been discussing maybe is to have some standard classes that can be put online with people teaching classes and also explaining what the data means on videos. And maybe we could organize, just like in the New York University, face-to-face workshops, but also completely remote workshops, also hybrid workshops where you have online videos, but then maybe experts are available for answering questions online. So we need to think of all of this. Of course, we need some funding for this. We need to have people available. It's a lot of work, but that's a minor amount of money, and I think it's easily doable. And I completely agree. We need to go in that direction.
Hi, Paulo. This is Reinaldo Rosa from INPE. How are you? Hello?
Yes,
Can you hear
sorry,
me?
there is an echo, and I cannot hear very well. Could you repeat, please?
Hi, Paulo. This is Reinaldo Rosa from INPE.
Yeah, oh, INP, yeah, INP, yes. Hello,
Okay.
yes.
Actually, I have a business question for you.
Okay.
Which are the requirements in order to have a shop in the open universe?
Which are the requirements to have what, sorry?
The shop. If you want a shop, a kind of service there, what do you call a shop in the many?
You mean to collaborate? Well, I'm not sure. Let me try. Let me see if I understood. When in the also Ulysses can explain to you probably better than me that I'm here. But in every country, we are foreseeing the existence. Every country participating or every scientific institution participating can provide an open universe node. And that is some computer infrastructure, some knowledge, and some, or even some data, depending on the local interest. So as a minimum, so maybe some virtual machine, something to participate. All you need is a computer and somebody who takes care of it. And if you have some particular interest, we can think of customizing to the local needs.
Okay, I got the point. So I'm going to talk to Ulysses here about that.
Yeah,
Okay,
yeah,
thank you.
yeah. Ulysses knows everything about this.
Yes, so
Thank you.
he explained to me a little bit the question, Paulo. I think what he was considering is, for example, if there is a project from INPE or from someone, or a project from the BRICS group for some data and some software applications, would it be possible to have it, for example, on the page where you see, when you type a source, you see all the services providing results of that sources? So I think that was the context of his question.
Of course, yes. The answer is of course yes. Any proposal, as I said, we are inclusive, and if you have a service or you want to have visibility to Open Universe, you are more than welcome. But we have to agree on an interface, but that's usually a simple.
Thank you very much, Paulo, and thanks for the talk.
Thank you. Thank you
We are
very
going. Okay, we are going for the coffee now. And but before we take the coffee, let's go outside and take the group picture just in front of the wall. That's the picture that makes our poster. And the coffee will be served just after the photo. The suggestion of the organization is that we take a picture of Takalani on the beach, and we just include it with the Photoshop.